Hey friends, welcome back. In the next 15 minutes, I'm going to demystify fine-tuning for large language models. We'll cover what fine-tuning actually is, the different approaches, full fine-tune, LoRA, adapters, PEFT, how to prepare your dataset, a high-level training pipeline, evaluation tips, common pitfalls, cost estimates, and a short demo plan you can replicate. If you're here to go from zero to confident, stick around and hit subscribe if you want more practical AI tutorials. Let's jump in. First, what is fine-tuning? In simple terms, you take a pre-trained language model and continue training it on a task-specific dataset so it performs better on that task. Think of it like teaching a multilingual translator some domain-specific slang. The base knowledge stays, you just adapt it. Fine-tuning adjusts weights so the model specializes, which usually gives much better correctness and behavior than prompt-only approaches when you have enough examples. Why fine-tune? Key reasons: improved task accuracy, better alignment to domain language, consistent output format, and lower latency when you replace expensive prompt-engineered chains. When to fine-tune? When you have significant data, even a few hundred to thousands of examples can help with modern methods. Need custom behavior or safety constraints, or require higher reliability than few-shot prompting gives. Okay, there are multiple ways to fine-tune. Full fine-tuning, update all model weights, parameter-efficient approaches, LoRA, adapters, and prompt tuning, where we only change a small subset of parameters or add lightweight modules. PEFT, parameter-efficient fine-tuning, is an umbrella term for these efficient methods. We'll compare pros and cons next. Full fine-tuning is straightforward. You keep the model architecture and continue gradient descent on all weights. Pros: maximum flexibility and often the best final performance. Cons: high GPU memory, long training, and you need to store a full copy per variant. Use it when you have ample compute and need maximal performance. LoRA stands for low-rank adaptation. Instead of changing big weight matrices, LoRA injects small, low-rank learnable matrices into attention or feed-forward layers. You only train these small matrices and keep the original weights frozen. The win: huge reductions in trainable parameters and storage, often tens to hundreds of times smaller, while preserving performance for many tasks. Adapters add lightweight bottleneck modules between layers. They're modular and can be stacked or shared across tasks. Prompt tuning keeps the base model frozen and learns a virtual prompt, small embeddings that steer model behavior. These are great for multitask scenarios and when you want to store many task-specific adapters cheaply. Dataset quality is often the biggest determinant of success. Steps: gather diverse examples for your task, clean and normalize text, ensure consistent label format, and split into train, validation, test. For instruction tuning, format examples as instruction, input, output. If you're using few-shot or synthetic data, be careful of label noise. High-quality, smaller datasets beat large, noisy ones for fine-tuning. Format matters. For supervised tasks, use JSON-L with fields like prompt and response, or the instruction, input, output trio for instruction fine-tuning. Tokenize with the model's tokenizer, and consider sequence lengths, truncate long context, or use chunking strategies. Also augment edge cases deliberately to improve robustness, e.g. adversarial examples, uncommon phrasing. High-level training steps. 1. Choose model and approach, full or PEFT. 2. Prepare datasets and data loaders. 3. Set training hyperparameters. 4. Train with checkpoints and mix precision. 5. Validate and log metrics. 6. Save and export the fine-tuned weights or adapter files. Tools: Hugging Face Transformers, PEFT Library, PyTorch, DeepSpeed, or Accelerate for optimization. Important hyperparameters: learning rate, smaller for PEFT, batch size, bigger helps but watch GPU memory. Number of epochs, often few for strong pre-trained models. Weight decay and warm-up steps. Use mix precision, FP16, and gradient accumulation to reduce memory footprint. Resource tips: LoRA adapters can run on a single A100 RTX 4090 for many tasks. While full fine-tuning of very large models may require multi-GPU setups or specialized services. Evaluate with task-appropriate metrics, accuracy F1 for classification, Blue Rouge for translation/summarization, but also use human eval, and instruction-following metrics for conversational agents. Always hold out a test set and consider adversarial examples. Use qualitative inspections and examples to catch hallucinations and prompt sensitivity. Common pitfalls: overfitting, watch validation loss, label leakage, forgetting base knowledge, and data contamination where test data overlaps pre-trained corpora. Best practices: keep a validation set, use early stopping, track experiments with logging weights and biases ML flow, version your datasets and adapters, and run safety checks for biased or toxic outputs. Here's a short demo plan you can run in a notebook. 1. Pick a base model from Hugging Face. 2. Prepare a small JSON-L instruction dataset, 500 to 2000 examples. 3. Configure PEFT with LoRA, set rank equals 8 to 32. 4. Train for 1 to 3 epochs with FP16 and gradient accumulation. 5. Evaluate on a holdout sample. 6. Export the LoRA weights and test inference. I'll link a ready-to-run repo in the description. Rough cost estimates. LoRA adapters on a single GPU, a few hours to a day, and under $50 to $500 depending on cloud rates and model size. Full fine-tuning of very large models, 100B plus params, can run thousands of dollars and need multiple GPUs. Always test on a small subset first to estimate runtime and scale up. Also, factor storage for checkpoints and cost of human evaluation if needed. Real-world uses: customer support assistants specialized to a company's docs, healthcare triage bots trained on clinical protocols, legal contract summarizers that follow strict formats, and creative writing models tuned to an author's style. Many businesses start with PEFT to iterate quickly and keep many task-specific adapters without duplicating full models. All right, quick recap. Fine-tuning adapts pre-trained LLMs to tasks. PFT methods like LoRA and adapters are efficient and practical. Dataset quality and evaluation matter most, and start small, iterate, and track experiments. If you want the demo repo, script snippets, and a checklist PDF, grab the links in the description. Smash that like button if this helped, subscribe for hands-on AI tutorials, and tell me in the comments what model or task you want me to fine-tune next. Thanks for watching. See you in the next one.